overkill, but it is a commonly asked topic on the Regents exam. We're going to spend 3 days on our last transformation. And this transformation is not a rigid motion, it's called dilations. And they're called dilations, and yes, we're going to spend 3 days on it. It is a commonly asked topic on the Regents. Before we hit up dilations, though, I do have one more vocabulary term for you. I'm pretty sure we have. We've done problems this unit where we've done like a reflection and a point never moved. Right? It just stayed right on that line because it was on the line of reflection. All right. I don't know if you guys remember any specific question like that, but I'm sure we've done problems where, okay, I want you to do this, but one of the points just stayed exactly where it was. All right. I'm going to give a name to those points now. Those points that never move are called invariant points. All right. They're points that do not move after a transformation. Do not move. Those are called invariant points. So we do what we're asked to do, but then all of a sudden, like point A just kind of stayed there. That's an invariant point. So I just want to make sure we're good on this. You don't need a graph. I've graphed it up here already. I want to take point B right now. I want you guys to tell me to do something. Reflection, rotation, translation, and B will stay right where it is on my graph. And let's get this out of the way. Don't be the kid that does the following. Let's do a translation of 0, 0. Let's do a rotation of 0 degrees or 360. Okay, let's not be that kid. Okay, and let's do a rotation around point B. It won't go anywhere then. No. Okay, let's get a little more creative here. Tell me a reflection, rotation, translation that I could do other than those lame ones where B is going to stay there. It's not going to move. What do you got over there? Okay, there you go. So if I reflect this entire figure over the y-axis, everyone agrees B is not going anywhere. Good job, Taylor. Yep. All the other points will move, great, but B will remain invariant because it won't move anywhere. Go to point D. Give me something I can do that point D is not going anywhere. And that would be a reflection over the x-axis, yeah. All right, so I just wanted to put a new vocabulary term to those points that just sit there and don't move anywhere. All right. One of my goals this year, guys, is to try to get you out of some middle school thinking. All right. Hopefully I've done a decent job of knowing, hey, when I have a triangle and you hear the word base, that doesn't mean the bottom. Okay. And when I say the word height, that doesn't automatically mean here down to the bottom. There could actually be 3 different heights, right? All right. I want to talk about dilations now. All right. Middle school, it was all what? Something gets bigger, something gets smaller. That was probably your entire middle school career. You were drilled to. You heard the word dilation. Something's getting bigger, something's getting smaller. Your teacher might have been, hey, it's kind of like your eyes dilate. All right, whatever. But I got a question for you now. We're in high school now. I got a question. I got point A up there. If I want to dilate point A, is that what's really going to happen? It's really going to get bigger. No, that's ridiculous, right? That's ridiculous. So I want to show you today what actually happens in a dilation. Because yes, things do get bigger or smaller, but I want to show you why they get bigger or smaller. In a dilation, I'll give you 2 things. I will give you 2 things. I will give you the center of dilation, which is that point right there. I will give you the center of dilation, and I will give you what's called the scale factor. All right, the scale factor. Can you make a little notation down here in that box? Sometimes, especially in your textbook tonight, this drives me nuts because I have no idea why they do this, but sometimes the scale factor is referred to with the letter K. Guys, I don't know. That's something I can't answer. No idea why. So you'll be given the center of dilation and the scale factor. So let me now show you what happens when you have those 2. So this one has a scale factor of 2. So what is actually happening to the points? Because they're not going to get physically bigger. That's ridiculous. Here's what's happening. Everybody see in my diagram here, A to the center of dilation has a certain distance. All right, we're not going to measure it, but it has a certain distance. Agreed? What the scale factor of 2 says is we're going to increase that distance. We're going to double that distance right now. We're going to double that distance. So do you see how O to A has a certain distance? I'm going to double that distance from O to A prime. So it's getting further away from the center. Okay, point A along with point B, C, and that's it, A, B, and C are getting further away from my center. So if you want to write some units here, if that's 4, that's going to be a distance of 8. Okay, the distance of the points is increasing. The point is not getting physically bigger. The distance is increasing. So when the scale factor is bigger than 1, all right, when the scale factor is bigger than 1, that results in the figure getting bigger because what's happening to the points? The points aren't getting bigger, they're getting further away from the center. Okay, so when a scale factor bigger than 1, the points are getting further away from the center. Can they get closer to the center? Absolutely, they can. Look at my second diagram. Notice my scale factor now is 1/2. So how do I know the points are getting closer to the center? If your scale factor is, now watch this, not less than 1, because we're not going to have any negative scale factors. A scale factor between 0 and 1. That's how I know the points are getting closer, which means the figures will get smaller. That's what I want you to pick up today. Guys, points cannot get physically bigger or smaller, but they can get further away or closer to the center. Let's actually dilate now. Let's actually dilate. I have point J on the graph. Can we just, because this is going to come into play in a minute, just make sure you put down what point J is. What is that, 3, 2? All right, you'll need that fact in a minute. Read part A. Read what we're going to do. All right, we're going to dilate it. The center is going to be the origin and dilate it by 2. So does that mean J is going to get closer to the origin or further away? Great job. Good job, first step. It's going to get further away. And make sure it's going to get further away going this way. It doesn't go on the opposite side. That's called a reflection. We've done those. All right, so it's going to get further away. How much further away? It's going to double its distance. But good news, I don't need the distance formula. We're going to use slope to do this. So from the origin to J, I'm going to call in my first person here today. From the origin to J, I go up and over how many? Up and over how many to get to J here? Let's start it off right. T, what's good? Up and over how many? Up 2 over 3. Everyone agrees? Up 2 over 3. And you need to double that. So instead of going up 2 over 3, we're going to go up 4 over 6 from the origin now. So up 4 over 6, you just dilated J. So is everyone good? I went up 2 over 3, but whoa, I got to double that. So up 4 over 6, or I don't know if anybody did this, you just went up 2 over 3 again from J. That's fine. Does it say, it says graph and state. So yeah, we got to state what J prime is here. J prime is 6, 4. All right, we all good? All right, now let's do it with a scale factor of 1/2. So where's J going to go? Closer or further away? Closer to the origin. Half the distance now. All right, so T just said, hey, up 2 over 3. You better cut that in half now. Instead of going up 2 over 3, we go up 1. And I know this is odd, but deal with it. Over 1.5. Yeah. Up 1 over 1.5. Yep. There's part B, J prime. And that's going to be what? 1.5 comma 1. All right, one more. How about a scale factor of 3? Now we're getting further away. We're tripling the distance away now, right? Triple. So going back to T's comment, up 2 over 3, triple it. Now we'll go up 6 over 9. Yep. Up 6 over 9. And there is part C's J prime. And that's going to be 9 comma 6. Are we okay on using slope though? That's not bad, right? Getting closer or further away. I got a shortcut for you if you want it. I got a shortcut for you if you want it. But I don't give the shortcut out for free. You guys are gonna have to determine what the shortcut is. And here's what I want you to look at. The original point we went from 3, 2, and the scale factor in every part. All right, look at the original point we started with, the scale factor, and what J prime ended up being. There's a shortcut. I don't have to do up and over all the time. There's a shortcut to get there. All right, so take a peek at J, the scale factor I gave you in parts A, B, and C, and what we ended up with for J prime. All right, if you don't need to do slope and triple it, double it, cut it in half. There's a way I could get the J prime coordinates a little quicker with the shortcut. Anybody see it? Anybody see my shortcut? What's up, Jesse?
Multiply the pre-image by the scale factor.
Yeah, hey, take 3, 2. Go back to part A. My scale factor was 2. If you multiply the x and the y by 2, what do you get? 6, 4. Okay? Part B, if you multiply 3 and 2 by 1/2, what do you get? 1.5 comma 1. Yes. But I want to warn you, it's an awesome shortcut, but it only works at one and only one time. If I'm dilating around the center or the origin. The center is the origin. This is the only time that it works. And again, let me just repeat what Jesse said. We're going to multiply the original coordinates by the scale factor. All right, so you guys decide. You want to use that shortcut, feel free. If not, keep using slope because there is an instance where we are going to have to use slope. Any questions on dilating around the origin? All right, well, unfortunately, you guys are in an above level math class, so we won't be dilating around the origin every time. You could dilate around another point. So instead of the origin, now we're going to take point J again, same spot, but now dilate around 7, 1. So everyone find where 7, 1 is. Okay. Find where 7, 1 is. That's our center now. Same question I asked you previously. Scale factor of 2 in part A. Is J going to get further away or closer to the center? Further away. It's going to double its distance. Hey, I can't stretch. It's this way, further away, not on the opposite side. We always go on the same side. All right, so who's going to do the up and over here with me? Boom, Alex, you're up. Now make sure, hey, when you go up and over, make sure you start from the center. Alex, starting from 7, 1, I got to go up and over how many to get to J? Up 1 over 4. This says a scale factor of 2. So instead of going up 1 over 4, we're going up 2 over 8 from the center. Up 2 over 1, 2, 3, 4, 5, 6, 7, 8. And that is going to be, let's see, -1, 3. Or you could go from point J up 1 over 4 again. It's up to you. All right, let's do the 1/2. Now it should get closer to the center. Should get closer here. Alex said, well, up 1 over 4. So everyone go up 1/2 over 2 for 1/2 here. So there's J prime. What was that one there? 5 comma 1.5. Is everyone all right? Am I going too fast? We all right? And you'll notice my multiply trick doesn't work here. All right, it does not work anymore because I'm not at the origin. And now let's triple it. What did you say, Alex? 1 over 4, right? So 3 over 12. 3 over 12. Negative 5 comma 4. Questions, guys? Dilating when it's the origin versus not the origin. All right, because these next couple problems you're just going to kind of take on your own here. All right, I'll put up my answer up here so you guys can check, but I'm kind of done with the teaching here today. So go ahead, you're going to dilate this triangle by 2, and notice it is around the origin. It is around the origin. So if you want to, you can take points A, B, and C and multiply them by 2. Or you can do slope from the origin, all right? You just have to graph the new ones. You don't have to state. Take your time. You do what's comfortable for you. So you go up 2 over 2, yep, and then you double that now. I get it. If you're going to go up 4 over 4, yes, you start right back at the center. You have to do that. Okay, everyone good on this one here? Making sure, because now the last one, and some of you are starting it already. Now we're going to dilate. Now it's not the, and I've been looking around here. Some of you guys are making the common mistake. Hey, B should not be on the other side of D, right? B should be further away going this way. A should be further away going this way. C should be further away going this way. All right, don't go on the other side. Don't go on the other side. Count your slope from D. So I'll do it from D to A with some of you here. So from D to A, I go down 1 over 1, 2, 3. The scale factor is 2. So double that. Instead of going down 1 over 3, I'll go down 2 over 6. Make sure you go from point D down 2 over 1, 2, 3, 4, 5, 6. And notice how A gets further away on the same side. Okay, this is not one you can multiply by the scale factor, all right, because we're not dilating around the origin, we're dilating around 1, 2. Start counting from the center. Start counting from the center. And it just says graph and label. Did I assign number 30 tonight? I did? Okay. Because I made myself a note here. You're going to need the distance formula tonight when you do number 30. If you're still working on that last problem in the notes, there it is up there. I'll come around, help you out if you need it. But if you got everything good to go and you feel confident, go ahead, open up the textbook pages. I'll come around if you need help. Not an easy topic here. I think tonight you guys got lucky.